Hi, welcome to Thermochemistry 2. My name is Dr. English, and today we're going to be talking about relating delta G to a phase change at equilibrium. Specifically, we're going to look at Enduring Understanding 6.d, which states the equilibrium constant is related to temperature and the difference in Gibbs free energy between reactants and products. So let's start off by relating delta G to phase change at equilibrium. The normal boiling point is the temperature at which a pure liquid is in equilibrium with its vapor at a pressure of 1 atmosphere. So if we look at this representation over here, we can see that we have vapor pressure above and we have liquid below. And we can see that the phase transition either goes from the vapor becoming a liquid or the liquid becoming a vapor. So this diagram basically represents the phase change. If we look over here at a vapor pressure diagram of 4 different liquids, we know that at a pressure of 101.3 kPa, which is the equivalent of 1 atmosphere, the temperature at which each of these lines intersect this vapor pressure is the boiling point. So we can look at water, and we can look at this point right here, and we can state at a pressure of 101.3 kPa, the temperature is 100 degrees Celsius, and water will go through phase change from a liquid to a gas. So at 100 degrees Celsius, this is our liquid phase, and this is our gaseous phase. And that relates to the other 3 compounds listed in this diagram. So what do we need to do here? We're going to calculate temperature when delta G is equal to 0. So we're going to start off by writing the chemical equation that describes the physical equilibrium between liquid and gaseous carbon tetrachloride at the normal boiling point. So all this really means is that we're going to write the formula for carbon tetrachloride, which is CCl4, as a liquid, and that's a little cursive L, and we're going to put a double arrow saying that it is reversible, and then we're going to just write CCl4 again as a gas. And this represents our physical equilibrium between transitioning from liquid to gas as it moves into becoming a vapor, and gas into a liquid as it condenses and becomes a liquid again. So what we're going to do is estimate the normal boiling point of CCl4 based upon thermodynamic data. Now, delta G is equal to 0 for the equilibrium involving the normal boiling point of any liquid. In any normal boiling point equation, both the liquid and the vapor are in their standard states. So that means we're going to be able to go look at thermodynamic data at the standard state. So the formula that we're going to use here is delta G prime is equal to delta H prime minus T sub B, and remember that little b right here just means boiling, the boiling point. Delta S prime is equal to 0, so we can rearrange this because we know that delta G at standard state is going to be 0 at equilibrium, so we can rearrange this middle part to find the temperature of the boiling point by looking at thermodynamic data for delta H and delta S prime. So if I went to my standard state table, I can look at this and I can say, all right, I know that I have this formula CCl4 as a liquid, a reversible reaction, CCl4 as a gas, and I can look up the values of delta H at standard state for this, and this is going to be negative 95.7 kilojoules per mole minus negative 128.2, and that is going to equal a positive 32.5 kilojoules per mole. Need to watch my labeling because we know the negative and the negative here become a positive. So now what I'm going to do is I'm going to solve for delta S at the standard state. So I'm going to find the value for CCl4 liquid, and that is 309.7 joules per mole Kelvin minus 216.4 joules per mole Kelvin. And when I take the difference of those two, I'm going to get 93.2 0.3 joules per mole Kelvin. Now the thing to realize here is that, of course, that this 32.5 kilojoules per mole is in obviously kilojoules, and this is in joules. So what I need to do is I need to take that joules and convert it into kilojoules before I really go any farther. So we're going to have 93.3 joules per 1 mole 1 Kelvin, and I need to convert that joules into kilojoules, and I know that there is 1,000 joules in 1 kilojoule, so that means these joules cancel. So when I work this out, it's going to be 0.0933 kilojoules per 1 mole 1 Kelvin. And now, based on this, I can take it into this formula up here and solve for the temperature at boiling point. So temperature at the boiling point is going to equal delta H at standard state over delta S at standard state. So I'm going to take my values, which is going to be 32.5 kilojoules per 1 mole, and divide that by 0.0933 kilojoules per mole Kelvin. And then we have our units cancel, so kilojoules will cancel kilojoules, moles will cancel moles. I'm left with Kelvin, which is ultimately going to flip up as we do our formula manipulation. And if I divide 32.5 by 0.0933, I am going to get 348 Kelvin. So this is an example of how you can find the temperature at the boiling point, where we know that delta G at standard state is going to equal 0 because we're at equilibrium during this phase change, and by using delta H at the standard state and delta S at the standard state, values to represent those, as long as we keep our units consistent, we can calculate the temperature at the boiling point.